Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi class, welcome back to SIC2006. Today we're going to proceed with lecture 9. It's a short lecture, but this is one of the important aspects of NMR which I need to address so that you see the vast usage of NMR spectroscopy, which is not just limited to elucidate molecular structure. So what do I mean by that? Today we're going to talk about motion. Now, as far as in terms of seeing the interpretation and the usage and the application of NMR that we have covered so far, it seems to be covering more on this molecular elucidation, meaning that if you have an unknown molecule and you want to elucidate it, NMR is certainly one of the most powerful tool to actually decipher the molecular structure. But NMR can do a lot of other things. There's so many other functions of NMR, and one of it is actually to detect on the motions of the molecules. At the molecular level, you're able to actually get some hint on what's going on with your molecule. And this is one of the abilities that I do want to address, so that you will know that there are so many things that NMR can do. And because of that function, so there are things that you want to understand, the intricacy of the behavior of a molecule. You're able to do that, at the molecular level. So why is that so? And you know that molecules are not rigid. Well, you are actually looking at the molecular structure. The molecules are continuously moving, so there's this internal dynamics. So you have these vibrations, and of course it depends on the motions, will depend whether you have many atoms or if the atoms are massive. So that's going to sort of like hinder the movement, so the movement will be slower. But if you have something which is lighter, like a hydrogen being the atoms, so you have these rapid local oscillations, which is called librations, as in the picture here. And so then there is also, when you have these symmetrical molecular groups like the methyl group, so you have this rapid rotation as well. So there's a lot of dynamics going on. Now the other kind of movement that also exists in molecules is the chemical exchange. So you have the making, breaking of chemical bonds, and then you have this different exchange conformation between one structure to another. And so these processes can also be detected via NMR. And if you see some kind of intricacy in the spectrum, that can also be attributed to this movement. And that's something that can be very useful when you have molecules that can have these processes, these chemical exchange processes. And so you have these rotations, you have this translation, and so on. So this is a good thing, because while you're looking at the structure, you're also looking at the structure, which seems to be like there's no dynamics in there, but you can also look at the dynamics part of it, and so that makes really NMR such a powerful tool. And so we're going to focus on chemical exchange. And of course, when the rate of exchange is slow, so you can actually see the separation of um, one conformation to another, and you can sort of like see that the distinctions, the two lines which corresponds to the chemical shift of the two environments. But usually by the increase of temperature, or maybe due to the purity of the environment, you can actually get in this case, increasing the temperature actually increases the rate exchange of the two conformation, and so you get this the coalescence, or the combination of the two lines to a broad line. and and in certain cases, if you increase the temperature further, you can actually have a sharp line there. And so you can actually account for this. You can actually calculate this via the time that it takes. And also you can also use the line broadening or the line width as part of the analysis of doing this chemical exchange. So it's not just, sometimes you have a molecule that you know the molecular structure, but this is one analysis that you can actually do to understand the chemical exchange process of the respective molecule. So, and this coalescence, and so the observed broadening is given by this equation. So this is just the measurement of the line width, and so it has to do with, of course, this the tau, which is the relaxation process, which is actually um, related to the line width and so on. But this is not the equation that I want you to focus on. I want you to focus on this equation. Okay, so in the process where you have this exchange, chemical exchange process, so the time when it takes two environments to actually coalesce to become a single line, it occurs at this time. So the time it takes to actually combine from two single peaks, combine to become one single peak, is equivalent to the square root of 2 over pi times this delta V. Delta V is just the difference between the chemical shift, and because this is delta nu, so this is in hertz, okay, not in ppm. This is in hertz. So if you have values which is in ppm, you have to convert that into hertz, okay, and you use the equation of the chemical shift equation to actually do that. So remember, this delta nu is in hertz. And so then you get the time it takes for the two peaks to coalesce. So what about the rate? Okay, this is time, the time it takes. So the rate will just be the reciprocal of this. So 1 over tau is going to be the rate it takes to actually coalesce. Okay, so this is the time, the rate will be just 1 over tau. Okay, the reciprocal of that. And so this is one example where you can see that the increase of temperature of this particular molecule will actually finally coalesce it to a single peak. And one of the classic example, we always have ethanol. So if the so this is something that we usually see in the what they call for the NMR spectrum for ethanol. But in what you see here in the figure A here, you will see that this is an example. If you have a pure ethanol, that means there's no water, so there's no exchange process. So you see that the peaks of the hydroxyl group is going to be influenced by that of the CH2 group. And this the CH2 group here, the peaks here are going to be influenced by the peaks of the alkyl group here and the OH group here. But and in between you have that. But once you have, for example, water, if so you see that the OH in the ethanol can undergo chemical exchange with the protons from water. So then you will have this very fast exchange. So you won't see the details there. So what you see is really the fast exchange between the water from the environment and the OH from the ethanol. So you get that this peak of the ethanol that you see. So this is when you have a pure ethanol. This is when you have actually water in the ethanol. So this is without water, dry ethanol, and this is with water. So you have the exchange process, so you can't see the detail there because the exchange process is very fast. So as I said, this is a very short lecture, but this is to emphasize that the kinetic process is one of the useful information that's given in NMR. And one of the kinetic processes that we just highlighted is on the exchange, the chemical exchange. And so there are many aspects of this. Now I want to leave today's lecture by just showing you that this may not be liquid state NMR. This is from solid state NMR. So this is one example that you can sort of like visually see that it is moving. So this is just to show that this is really a liquid crystal sample in a solid state NMR. And what happens here is that the sample is actually rotated 90 degrees to the magnetic field. And so because it doesn't want to stay there, the magnetic field is very strong. So now it's showing that what we call the director of the liquid crystal is being pulled back to the original state, which is along the magnetic field. So this is when the director is actually perpendicular to the field, magnetic field, and this is when it actually gets aligned back to the magnetic field. Now you don't have to know this experiment. This has got nothing to do with your what's going to be tested. But what I want to show here is that if you can sort of like see, like visually, we can't see the dynamics, as in per se, molecule wise, but you can see here from the NMR spectrum, you can see sort of like the movement via the location of the peaks here, showing that it is responding to the very strong magnetic field. So you see the dynamics of that. And so clearly this is one very powerful tool, and so many different angles of the NMR can be explored and to actually understand your molecules better. Okay, so that's all for today's for this lecture. So I'll see you in the next lecture. All right, thank you and take care. Assalamu alaikum.